Awesome. So, hi guys, welcome back to the ACM AI Intro to Machine Learning beginner track. This is workshop 3, and we're going to be talking about linear regression this time. Just a quick note, here's the feedback form. It's on the slide, and the link to the slides is in the feedback form. I'll drop it down in the chat in a second. And of course, if you haven't joined already, feel free to join the ACM Discord, where we actually discuss a lot of the stuff that we're actually teaching, and the recordings and everything else is posted out there. So definitely do check that out. So before we dive in to linear regression, a quick plug for AI Labs, which is one of ACM AI's offerings. It's a one-off event where we're going to talk about the modern applications of AI. So a lot of people actually have heard of AI and they want to get into AI and machine learning, but they don't exactly know where to start. So we're hosting a sort of introductory, an incubatory session for people to delve into AI, understand the modern applications, how they can get involved. So this is going to comprise of some theoretical, some hands-on stuff, and definitely do check this out. Apart from that, if you can't make it in person to Engineering 4 Maxwell Room, of course, then we will be streaming this live as well. And again, the link will be in the Discord. So definitely do check that out. As we progress, since we, of course, know that UCLA is planning to go back in person, we actually wanted to know how many of you are going to be interested in an offline offering of the workshops, whether you prefer the online and recorded version, or you'd like to go back into an in-person, offering of the sessions. So I'm going to launch a quick poll. Yeah. And if you could just fill this out. Awesome. All right. So I see we have mixed interest, although I think we're leaning more towards yes. So we'll be looking into this over the next couple of days, next couple of weeks, and we'll keep you informed for sure. So now, before we move in, does anyone have any questions from previous workshop offerings, from lecture 2? If you want us to go over something again, we can definitely do that. Feel free to interrupt me at any point of time. Feel free to drop stuff in chat, and of course, if you're uncomfortable, just DM me. And yeah, I don't see anything, so I think we can get started. So today's content. So just for reference, last time we looked at classification. We looked at k nearest neighbors, which is actually referred to as classification in machine learning. And this time we're going to be looking at something called regression. So a lot of you might ask what the difference between classification and regression is. So classification is a system architecture in machine learning where we're actually trying to predict a label for the data. Okay, so we input a bunch of stuff and we train our model, and then it can label the next bit of information that we give it. In regression, however, what we try to do, and regression is it's by far one of the most widely used architectures in machine learning in general, and we cover this in the next couple of workshops. We'll be taking a look at different kinds of regression. We'll be looking at linear regression, we'll be looking at logistical regression, we'll be looking at multi-class regression. So when we talk about regression, now a basic introduction to regression is that instead of a label, which we did try to predict in classification, we're trying to predict a quantity. Okay, and that's the major difference between classification and regression. Today we're going to be looking at linear regression, where we'll be looking at regression in the form of a line, and we'll be exploring how we can use that to predict different quantities based on the input that we're providing. So today's content, we're going to start off with a motivating example. We're going to talk about building an intuition in general, taking a real life example. Then we're going to be diving into a little more formal definition and hypothesis functions. And after that, we're going to have Claire take over, who's going to run us through the math, which is actually really interesting. And this math is something that's actually pretty useful and pretty basic to understand. But of course, it might seem a little intimidating at first, but we're going to hold your hands through it, and we're going to do this. And after that, we'll be looking at the loss function and gradient descent, and we'll be going through an actual real life demo so we can get some hands-on experience and understand how coding up a linear regression model works. So a motivating example, how well will Joe Bruin do on his midterms? Now, of course, it's week 4 and we're going to be having our midterms soon, maybe this week, maybe next week, early week 6. But since all of us are going to do on our midterms, I want to ask you, okay, if we want to predict someone's midterm performance, what sort of information might be useful? Right? What kinds of attributes, what kinds of factors are we going to be looking at, which can tell us how good someone is going to perform in their midterm? Feel free to unmute. If one of you could just unmute and tell me, that would be great. Or just drop in chat if that's more convenient. Awesome. So Gabe said past performance on midterms, which is, again, an excellent example, and the hours spent doing homework. Now, these are both quality examples, Mark and Gabe. Thank you so much. So when we look at information that might be useful, we look at features. Okay. So the time spent studying, the lecture hours attended, the amount of homework that you've done, how well the professor grades, or all of us often go and do and work before we choose our professors to see how well they grade the midterms. So yeah, that of course counts as well. And what we do is we call these bits of information about the student and the scenario in general, we call them features. Okay, now features is a hot word that we're going to be using through and through. So a feature, in short, is something that our target depends on. So what we're going to look at here is, so we're going to look at a few phrases. Okay, so we're going to look at what a target is and what a feature is. Now, in this scenario, for instance, okay, where we're looking at midterm scores, and we're trying to predict what someone's midterm score is going to be. So what we're doing is we're looking at specific bits of information called features that affect the midterm score, which is the target. So like you could see in the third point, the midterm score of the student depends on specific features. So the midterm score, which is the target, depends on features like the amount of time that you put in, the amount of lecture hours that you attend, amongst other things. So what is the relationship between the features and the target? So when I say, I attended X amount of hours for a specific midterm, in a specific class for a specific midterm. So that clearly is directly proportional. The more number of hours I spend attending in class, the better the chances of me doing well in my midterms are. So that is called a positive correlation. So there are two types of correlations. One is when we talk about direct proportion, where if we do one thing and we do it for, doing one thing leads to an increase in one attribute leads to an increase in the target. For instance, if I attend office hours for more time, the chances of me getting higher marks are more. So that is a direct correlation. That is directly proportional. On the other hand, the amount of hours I might spend, probably gaming, if I do that excessively before a midterm, I might not be able to focus. And that creates an inverse proportion here. So that is a negative correlation where if I game for more time, the chances of me doing on my midterms are maybe slightly lesser. So we're looking at those kinds of things. So just to review the slide, we have features and we have a target, and the features and target have a relation which can be positive or negative. So before I move on, does anyone have any questions? Because this is going to be fundamental when we move forward trying to understand the next few slides. Feel free to unmute or just drop it in chat. Okay, then. So how do we represent our data? So in this slide, what we're going to look at is the representation of data in general when we're trying to, think of linear regression as a concept. So in this really small data set that I've provided here, we have rows and columns, of course, and each row represents the information for one student in our data set. So student 1 has spent this much time studying, this much time attending lecture, this much, and the first column talks about his homework average. Okay, so each row represents the information for one student. So the number of students we have is the number of rows that we'll have in the data set. And each column represents one feature. So we talked about features. You guys gave some fantastic examples of what features are. And each column, except one, talks about one feature. All right, so the homework average, the study hours, and the lecture hours, these are features, so these are columns. And the one column that's left is the target, which is the list of the midterm scores. And this is actually what we're looking to predict. Okay, so here the target is, of course, the list of the midterm scores. So what we're trying to do, we've created a data set where for every student, we've talked about different features, what the value of those features were, how many hours they studied, how many hours they attended lecture, and what their homework average was. And based on that, we have, of course, the list of midterm scores. So we're trying to create a correlation here. So this column, the last column, is called Y. Now, why do we call this Y? Okay, we call this Y because we're talking about linear regression. When we're talking about linear regression, we're talking about straight lines. And a lot of you might have heard of Y is equal to mx plus b. So that is kind of the the idea that we're hinting at here. As we progress, we're going to be using Y is equal to mx plus b in a different format in a lot of ways, all through linear regression. So for now, just know that we call the target column Y. All right. Also, if you can see, like right now, we've talked of a positive correlation. So when the homework average was the highest, which was 95%, and the number of hours studied was the highest, and the number of lecture hours attended was the highest, we get the highest midterm score, which is 90. All right. So that's how it works. This is how a positive correlation works, because this is directly proportional. Now, how exactly do we model this relationship? Okay, so we've looked at a data set which has rows and columns, which has the targets, which has features, which has details about each student. Now, how exactly do we model this relationship? All right. So one way is to use a linear model, which is what we're going to do here. So now, what are the parameters of a line? When we talk about the parameters of a line, the equation of a straight line in math is y is equal to mx plus b. So those here are the parameters. All right. So when we talk about pattern recognition, I'm going to delve a little more into the parameters soon. When we talk about pattern recognition, that's what we're trying to do here with machine learning in general. All right. We want to predict the midterm score of the student given certain features. Machine learning helps us find a pattern that relates the target and the features. So when we feed this data set into the model doesn't know if it has a positive correlation or a negative correlation, or how much each feature should be weighed. Now, we don't know that initially. We're just giving it a bunch of data and we're asking it to predict a quantity given a different set of data, right? So we're trying to calculate the midterm score based on the data that we've given. So in this case, the pattern is determined by the parameters of a linear model. So coming back to the parameters, okay, there are a bunch of parameters. So there's the slope, and then there's the bias. So y is equal to mx plus b. All right, y is the target, like we discussed before. M, which is the slope, is so there's m, which is the slope, which we'll come to soon. Okay, we're going to talk about weights soon. And then the bias, which is the y-intercept. Now, a few of you might ask what a bias is. And so a bias in machine learning or in statistics in general is the difference between a predicted value and the true value. All right, so a lot of times when we talk about bias, we see that, machine learning, our algorithms or our architecture might sometimes have a little different predictions which are slightly off due to some parameters which have skewed the data. So there is a bias that is created. There's this inherent bias. So we try to get rid of it later on, which is the y-intercept. All right, we'll come to that. Now, machine learning, this is the old-fashioned way. So a lot of you who have done computer science before, some of you are in computer science 31, some of you, if you've coded in any programming language ever, how traditional programming works is that there's the data, okay, there's just data, and there's a program, and there's some sort of computation that happens, but we write this program, we provide this data, and then we get a bunch of results. It's as simple as that. However, when we look at machine learning is slightly different, okay? So in machine learning, we're taking in data and we're throwing in data, and we're also throwing in results, all right? So instead of having the results predicted initially, we're feeding in a bunch of results. So we have data and we have results, and a computation occurs, and then the machine tells us what the pattern is, the pattern or the model. So we come up with a trained pattern or a model based on the data and the results. So that's what machines are really good at, right? They're great at actually identifying patterns. So we use this feature of machines to actually take in data and results, provide a pattern or a model, which we can use to further predict results. All right. So before we move on, does anyone have any questions? All right, so I'm going to move forward. So let's just formalize what we've learned here. Okay, so right now we've just looked at an example where we take in, features that someone's midterm performance depends on, and we've tried to understand all the concepts behind that. We've looked at what features are, at what targets are, at how lines work. Now we're going to formalize this up a little bit. All right. Yeah. So let's talk about the hypothesis. The hypothesis is one of the greatest functions, one of the most important functions that we're ever going to talk about in machine learning. So a hypothesis is depicted by y hat. All right. You see this thing here? It's called a y hat. And this is, in short, the function that outputs the score given the features as input. So we discussed what features are. So we throw those features into this function and we get an output. We get an output, which is the score in the midterm. So this is exactly what we're trying to learn. Okay, like I said, in machine learning, we actually throw in the data and the results, and we come up with a function. So in this case, that's the hypothesis function. All right. So the input features, which are x1, x2, so on till xn. Now, when we talk about input features, we're talking about features like, the ones that we discussed before, like the number of hours that you put into studying, the number of office hours that you attended, the amount of sleep that you got before an exam. So all of these are the input features. So I'm telling a model that, hey, if I sleep this much before a test, if I put in these many hours studying, these many hours doing homework, then can you tell me what my score is going to be? Okay, and that's a great way, It'd be great if a machine could just tell me that, look, now just put in a bunch of hours and you're going to get an A. But that's what we're trying to work on here. Okay, so input features are the values that we plug into y hat, and our goal is to determine the y hat itself. So what we're trying to do is build a mathematical function, okay, y hat, and in the bracket that you see, we've basically thrown in the input features. Now we're going to try and determine what this is. So how do we use our linear model? Okay, we've talked about what the linear model is going to look like, but how do we use it? We have input features, and we want to use a linear model for y hat. Okay, y hat of x is equal to, okay, so a lot of you have seen y is equal to mx plus b, and this is in a way an expanded form of that. All right, we're taking in w's and x's, and here w is the weight. So we're going to come to that, but in short, it's pretty intuitive. Okay, a weight is basically the amount of importance that I'm trying to give to a specific feature. So some of you might say that, look, the number of hours I attend is important, sure, but does the number of classes I have the number of classes that I'm attending actually affect the model itself? So of course it does. Okay, now it's not easy to study for a midterm when you have 10 other classes that you're taking. But what we're trying to look at here is that it has a certain amount of weight, definitely not as valuable as the number of lecture hours I'm going to or the number of hours I'm doing homework, but it does have a value. So a weight basically gives in a specific amount of, of value, so an emphasis on one particular feature. Now, each of the weights, W1 through Wn, determine how much a particular feature affects the output. So the W is going to have the weight of what we're looking at, and the X is going to look at the input feature itself. So it's the value of an input feature into the weight of an input feature, the weight of an input feature being how important it is. And we multiply that, and at the end, we add the bias. All right, we add the bias to get our function, the hypothesis function, y hat. Now, does anyone have any questions?
Is there like x1, x2 term, like, for example, if like two features say like it like affect each other? Like, for example, like office hours and sleep, well, maybe if you spend more time studying, you'll have less hours to sleep. So they're not like mutually independent, right? Or are we just considering cases where all the features are like independent from one another?
Great question. So for now, we're going to be looking at them as independent features. But of course, as we expand further, as we progress, we'll also be taking a look at how these features affect each other. But for now, we're taking independent values. We're taking an independent number of hours and an independent number of, office hours attended or the amount you sleep. All right. Does that clear up your question?
Yeah. Thank you.
Awesome. So now the weights can be negative as well. A high negative weight for the number of classes might negatively impact the score. So what this means is, in general, if there's a high negative weight, so I have a high number of classes, okay, that will negatively impact my score. So how this works is, again, this talks about correlation. We looked at positive correlation and negative correlation. So positive correlation will have a positive weight because the value is actually going to be higher and it's going to be positive. But when we're looking at, a negative correlation, we're going to be looking at negative weights. So we're going to be looking at how something might actually, hinder my actual performance on the midterm. So something like the number of classes that I'm taking, if I'm taking 15 classes, which I would not recommend you do, if I take 15 classes, that's going to cause a problem, all right? That's going to negatively impact my score on my midterm. So now coming to weights specifically. Now the weights W1 through Wn and B. Okay, all of these, now here's an interesting thing. Okay, they're learnable parameters of our model. Now what do learnable parameters mean? Learnable parameters are parameters that we're not actually entering. All right, this is something that the machine is figuring out on its own. This is something that constantly changes throughout the algorithm and constantly changes as we enter more and more data. So a learnable parameter is something that we're not entering at all. This is something that the machine is going to figure out. The machine is going to look at this. The machine is going to try and develop patterns, and it's going to consistently and continuously learn. So I might provide a bunch of data, and then I might provide a bunch of data which is, in a sort of way contradictory. So that might change the weight altogether. So the weight is dynamic. The weight will keep changing over time. So of course, in the hypothesis that we looked at, we can change the function by changing the values of the bias and changing the values of W1 through Wn again. So the bias is also a learnable parameter, and it is also constantly changed based on the data that we're providing to our algorithm. And what we're trying to do is find the best possible weights for our model. So we look at huge amounts of data, and we just try to identify what the correct weight would be for the features that I'm providing. All right. So initially, my system might think that, the number of hours I sleep is actually not as important, but then suddenly there's a strong correlation. If I'm sleeping for more hours, if a student is sleeping for a lot of hours, is well rested before taking the test, they're having a better performance on the midterm. So the machine is automatically going to weight up. Okay, it's going to have a greater weight. It's going to be able to take in that value more seriously. So it'll have a greater weight. It'll have a greater impact on your performance. Looking at the model itself. So now, of course, an overview. We have y hat of x is equal to the weight of x, into x itself. Then the weight of the second x into the second x, and it goes on, and then we add a bias. So in machine learning, we often use matrices because matrices are very, they're short. You can just put in a lot of information. You can represent it in a very compact way. Okay, so we use matrices. So this is this is a horizontal array. This is a vertical array. And how we process these matrices, for some of you who might not, know how matrix multiplication works, it's very simple, all right? It's just this, which I've compacted down into this. So x1 times the first weight, x2 times the second weight, x3 times the third weight, and so on. And then we just add the bias. So I'm representing this array as capital X, and I'm taking the dot product with a capital W, which is the vertical array. And then I'm adding the bias at the end. So we've taken the dot product of X and W vectors, and then we've added B, which is the bias. Any questions? Awesome. So let's talk about the parameters again. Now, this is pretty much what I said, just formalized a little more. An input X is an n-dimensional vector for n features in the example. Now, of course, I should preface this by saying that we've only looked at this in a two-dimensional space so far. Of course, if we look at this in an n-dimensional space, we have an n-dimensional vector. So our vectors change based on the number of dimensions that we're looking at. So in 2D, what we have is, just a second. Yeah, we have a two-dimensional vector. So we're looking at x1 through xn, which is a horizontal vector, and w1 down to wn, which is, again, an n-dimensional vertical vector. And the bias b is a real number. We've already talked about what the bias is. Now, a quick polling activity before we move on to the next section and we look at the math. What feature do you think would impact your midterm scores the most? All right, and I'm going to launch a poll here. Yep. So which one feature do you think will have the greatest impact on your midterm score? Awesome. So what we have here is most people picking difficulty of the exam, to which I can just say definitely review your professors on Brew and Walk. So yeah, definitely what we're looking at here is the features that would impact your midterm scores the most. So how I would put this is definitely the difficulty of the exam and the hours I spent studying for the midterm. I'd say that these two should have the greatest weight, because historically I've seen that, and all of us have just observed that these two things will have the greatest impact. Now, of course, the number of pets you have might sure, it might impact you, maybe you want to cuddle with your cat before the exam, maybe that helps you perform on the exam. But what we're trying to say here is that the hours spent studying for the midterm and the difficulty of the exam in general actually, represent what we're trying to look at in a better way. Of course, the number of classes we take and the number of hours we sleep before also have an impact. So all of these are going to be given weights. So when we actually make a linear regression model, we take all these features, we give them different weights. So like you guys have chosen here, the difficulty of the exam is going to have the highest weight, followed by the hours spent studying for the midterm. And then I would presume the number of classes taken and the amount of sleep I've gotten before the test. And lastly, the number of pets that I have. So when I put all of these things together, I actually get my y hat, which is a nice long function of x, w, and the bias. And we're going to dive a little more into the math, and I'm going to let Claire take over. But before that, if anyone has any questions, feel free to unmute right now. Or, of course, drop in chat. Awesome. So I think we're ready to hand it off. I'll stop sharing.
All right, can you see my screen? Let's talk math.
Yep, it's visible.
And I'll begin. So let's go a little more into the math of what we just discussed. Maybe it will help you visualize how exactly these weights and biases change. So a quick refresher on a neat little thing called derivatives. You might remember, or maybe not, that the derivative of a function will tell you the rate of change of a function. more importantly, at least to us, if the derivative is positive, that's how we know that the function is increasing. Or if the derivative is negative, then the function is decreasing. So if we look at this graph on the right, the green line kind of represents the derivative at this point in time on the graph. And because the slope of the derivative, the slope is positive, that's how we know that the graph is actually going to increase. So let's continue on that, which is partial derivatives. To take the partial derivative of a function, at least for an example, with two variables, x and y, with respect to x, what we do is we take everything with y and we make y a constant. And then we just solve it as if it was a single variable function. So for example, we have function of x and y, which is 2x plus 3y squared. So if we're taking the partial derivative with respect to x, we take y to be constant. And now 3y squared, the whole thing is now a constant. So the derivative is 0. And the derivative of 2x is just 2. So the partial derivative of this function is 2. Now we can do this with other variables, such as y in this case, by taking x to be a constant. So now 2x, the whole thing is a constant with the derivative of 0. And 3y squared, the derivative of that with respect to y is just 6y. So now we have our partial derivatives for each variable in the function. Now, why does this matter? Well, partial derivatives inform us of how much of an impact each parameter or each variable has on the output. Now we can expand this to more than just two variables. For example, a function of x1, x2, etc., xn. And we just need to make every other variable as a constant, except for the variable we're trying to derive it in respect to. And then we just continue on as normal. So now, to calculate a gradient, well, what is a gradient? It is merely a vector of the partial derivatives of each variable in the function. So with a function of three variables, x, y, and z, a gradient would be a vector containing the partial derivative of x, the partial derivative of y, and the partial derivative of z. So we can go through an example really quickly here. A function of x, y, and z is equal to x sine y plus 2z cubed. So now the partial derivative with respect to x would be making y and z constants. So x is now multiplied to a constant, therefore the derivative is just a constant itself. And 2z cubed is now a constant. So therefore the partial derivative with respect to x is just sine y. Now, if we take the partial derivative with respect to y, we now have x and z is constants. Therefore, the partial derivative of a constant times sine of y is said constant times the cosine of y. And again, the 2 times z cubed is still a constant and the derivative is 0. With z, x sine y, the whole thing is now constant and the derivative is 0. So the derivative of 2 times z cubed is just 6 times z to the second. So the gradient would just be a vector of all three of those partial derivatives. So let's see if I can actually start a poll or if someone can help me start it. Okay, there you go. Oops. There you go. So what is the gradient of f of x, y, and z is x squared plus y squared plus z squared. I'll give it a couple more seconds. Oh, never mind then. Okay. Well, all of you guys got it right. The reason why it's not b per se is because remember, the gradient is in the form of a vector that contains all of the partial derivatives. Okay, let's continue then. Oh, before we go on, does anyone have any questions about how to calculate gradients? Okay, then let's continue to the loss function. Now, in order to continuously improve our model, we actually have to know how well we're doing. Otherwise, we don't actually know how to improve it. So how do we see how well we're doing? Well, we just use a loss function. So a loss function will tell us how much error our model's predictions are compared to the actual values of the target. So one example of what a loss function looks like is mean squared error. Image, there you go. So this is kind of what the function looks like. As you can see, the loss output with respect to these predictions is based on, we have the actual target value y for a particular prediction minus our predicted value, and then we square it, which is why it's called squared. And then we take the mean of all of these squared errors, which leads to the name and also gives us a loss. So we have y actual target, y hat is the predicted, and the difference between that is called the error. And we iterate over I, which is the I guess, training sample. So as we just saw before, the loss function depends on the predictions of our model, which is y hat. Now, y hat itself is based on, as we saw before, the weights and biases. It was W1, X1, W2, X2 plus B at the end. So therefore, the loss function is also indirectly a function of the weights and biases of our model. So here's another reminder for you here. So we just learned that loss inadvertently depends on our weights and biases. And that's how our model gets better and better, which is by updating its weights and biases. So ideally, we'd want as small of a value, as small as an output from our loss function as possible, which means that our model is doing well, is predicting things correctly. So therefore, our model is trying to find the weights for which the loss value is the smallest. So that begs the question, how do we do that? Well, here's how. Now we're going to go into something called gradient descent. Here's some visuals for you really quickly. So let's take an example of single variable gradient descent, where the f is a function of just one variable, x. So as we saw before with derivatives, we get an indication of whether or not our function is increasing or decreasing. So if the derivative is positive, we know that the function is increasing. So if x increases at this point, we know that the function will increase. Because we want to get the minimum of f of x, we actually want to go the opposite way and decrease from x, because now we know that we are decreasing f of x. And similarly, the other way around, if the derivative of the function is negative, we know that the function is actually decreasing. So we want to continue to decrease it. And how do we do that? We increase x. So here's an example right here. Let's say at this point in time, the derivative is positive and we are trying to get down to the minimum. So therefore, we'd want to decrease x. at this point in time. So to emphasize a little bit more, we're trying to minimize the value of f of x. So therefore, if the derivative of the function is positive, we want to subtract something from x. And if the derivative of the function is negative, then we want to add something to x. So how do we do that? Well, we'll use the derivative itself. But remember, we actually want to do the opposite of what the derivative tells us to do. So we can do something like this, where the new x is x minus alpha, which is right here, times the derivative of x. Now alpha is just a constant that scales how much the derivative impacts the step, I guess, and we'll call it the learning rate. Now, let's take a look at what happens if we try and do the same thing, but with more than one variable. So in case you remember, we have the gradient from before, which is a collection of the partial derivatives of all the variables. And what that gets us is the direction of steepest ascent. However, if we go in the same direction, we will increase the value of the function, but that's not what we want. We want to decrease the function, so therefore, we go in the opposite direction. We take the gradient and we do the same thing as before with the derivatives, something like that. And then we use it to step down, and we call that gradient descent because we're using the gradient to descend down the function. So to recap, now that we have more than one dimension, I suppose, x is now a vector of many x1, x2, and you might recognize this as the features from before. And the gradient now is also a vector. As we discussed before, the gradient has each of the partial derivatives of each variable. So therefore, we can update the x vector in a similar way to a single variable function. But now we just use the gradient vector and multiply it by our learning rate. And then we use it in a similar way. If the gradient is negative, notice that x will increase, and vice versa. If the gradient is positive, then x will decrease. So that's the opposite direction that we were talking about before. To conclude, I suppose, gradient descent is taking steps, step by step, to minimize the loss function. So the loss function is what we're trying to get the lowest value of. And with each step, you can see there's x's on this image. With each step, we're revising our weights and biases so that when we start to predict again, hopefully our model will be more accurate. And by updating our weights and biases step by step like this, then hopefully we can get the most accurate model that we can possibly do. And with that, I think I'm handing it off to Sudhanshu. Right?
Yep, sounds good. Let me do that. Cool. Can you guys see my screen?
Yes.
Nice. Okay, so yeah, great. Yeah. So at this point, right, we have a few different moving parts. We have this algorithm, gradient descent, which allows us to minimize something. And I want to bring us back to what we're trying to minimize. What we're trying to do is minimize our loss function. So what we're going to do, we're going to take this gradient descent algorithm, we're going to take all this knowledge and apply it to that loss function. And again, let's take another step back. What does the loss function help us do? It helps us get our predictions as close to the true values as possible. So to sum it all up, we're taking gradient descent, applying it to our loss function, which is applied to our predictions. So therefore, gradient descent makes our predictions as good as possible. So here's the flow of logic. What is the function that we want to minimize? The loss function. We want as low a loss, as low as an error as possible.
What are the weights of this function? Like we discussed, the loss function is simply a function of the W1 through Wn and the bias. So we want to essentially compute the gradient according to these parameters. When we apply gradient descent on the loss function, we calculate the gradient of its parameters. Therefore, we calculate the gradient of these W1s through Bs. And we simply update these. Like Claire discussed, we want to iterate through these one by one and essentially update them sequentially. And the way we do that is by taking the derivative with respect to each and every one of these weights and biases. Now, look, this formula looks a little scary. It's really not that bad. Don't worry. If you want to go home and derive it, it's actually not that bad. We have a link to the derivation. But what I want you to take from this is the general sense of what's happening here, right? Let me try and point. That did not work. Never mind. So hopefully you can see my mouse here. But what you're going to do is we're going to take our loss function, which is over here, and we're going to take its derivative with respect to each of the w's. What does that mean? That means that we're going to figure out how much each of the w's actually affects the loss. It's kind of calculating the impact each of the w has. What we're going to do, it gives us this fancy looking formula, but all you want to do is subtract that value from the old value of the w. So we calculate a gradient and subtract it. That's gradient descent. When we don't do this once, we do it continuously. We subtract the value, get a new value, compute the gradient again, subtract the value, subtract the value, compute the new value, subtract the value, compute the new value. We do this over and over and over again, thousands of times, millions of times even, and we get the best possible w. I mean, something very similar for b over here. We just calculate the gradient of the loss with respect to b, which means we calculate the impact of b on the loss. Once we do that, we simply subtract that value from the original b term. And that's how gradient descent works. It just subtracts the value again and again and again until you get the best possible value. The cool looking animation we had here simply means that we keep subtracting and we keep finding the best value until we get the lowest loss possible. Okay. And let me, great. Yeah, and we have a link to the full derivation of this formula over here. If you're interested, please check it out. It's pretty cool. And yeah, are there any questions about that point?
Can I ask a question, please?
Mm-hmm.
So like in order for this, like, I guess this is like an algorithm, right? So in order for this to like be able to subtract and minimize the loss gradient as like many times as possible and compute this as many times as possible, does that mean like new data has to be fed in for that to be computing?
No, so what happens is the data remains the same, right? And let's say given this data, we first have some random w's and b's. What we're going to do is we're going to calculate the gradient, this term over here, for those w's and b's. Once we have that gradient, what we're going to do is we're going to update those w's and b's. When we've updated them, we get these brand new parameters. That becomes the new information, so to say. Once we have those new parameters, we once again go and calculate the gradient, and then we repeat the process.
Yeah, so it's kind of like a guess and check type method where like the first times like they're guessing what the W and B are, but then like they check to see how much of a loss it is, and then the minute they like minimize that loss by subtracting, and then they just do that over and over until like the loss becomes really like small.
Yeah, exactly. That's actually really well said. That's exactly what I said.
Okay, thank you.
Yeah, of course. Any other questions? Okay, awesome. Let's move forward. So, so something interesting comes out of this whole thing, right? We've done a lot of really, sort of abstract stuff. We've done a loss function, done gradient descent. We made a hypothesis. What's really cool is if we formulate our problem like this, if we construct our algorithm like this, what it gives us is a line of best fit. And that's completely provable that it gives you the line of best fit that you may have looked at in high school in algebra. You may have learned a formula for this. But what happens is that After all this, it gives you the best possible value for a linear bit of data, right? And minimizing the loss function is sort of thought as fitting your line to find the best possible value. So in this example over here that we have in the animation, this is linear regression with a single feature. So the single feature is X, we have a single target Y, and all we're doing is trying out different values for the line until we find the best line that is possible. And another plug, the second to last workshop of this quarter, we're going to implement this whole thing from scratch, and we're going to actually implement the entire algorithm that we just discussed. Should be pretty fun. And a quick note, which is good to mention here. We discussed last workshop as well about how we have a training data and we have a testing data. Now, the training data is what we use to perform our gradient descent. It's what we use to compute our loss, compute our gradients, and do that over and over again. But what we have done right in the beginning is kept aside some of the testing data. The testing data is never seen before by the model. So once we're confident that, hey, our model has been trained, it has learned, and it has the best possible parameters, we're going to take that testing data, try it out on the model, and see how well it performs. And that truly gives us the accuracy of our model and determines how well it's done. So that's just a little aside. It's more of a implementation level thing that really matters in practical use cases. Okay, cool. Any quick questions about these couple of slides? Okay, sounds good. Let's move forward. So the good folks over at, I think, Teach LA have made this really nice gradient descent visualizer, which I'm just going to click into. So we have the link over here, and you can just click on Playground. And what they've done is they said, you can give us any function you want. You can give us a starting point, and we're going to visualize how gradient descent works, which is extremely cool, of course. So we have this function, x squared plus x. We have some starting point, x is equal to 5 over here. And what we can do, we can click setup, and we can just actually iterate. So I'm going to actually zoom in maybe a little more. And we can say next iteration. So you can see it's moved along this curve. Next iteration, moved along the curve. And exactly like we discussed, it keeps computing the gradient and keeps moving down along this slope until it finds the minimum value. So it's just a cool little visualizer. You can definitely try it out. We can try different functions. I don't know, x cubed, next iteration is not as good, So you can try lots of different functions and keep trying to minimize it using gradient descent. Yeah, so it's a cool visualization. Definitely check it out. How do I get back to full screen? There we go. Awesome. So the last section of this workshop, as usual, is going to be a code demonstration. And we're going to show you how to implement a linear regression model using Scikit-Learn. And if you want to click on the link, someone could post it in the chat. We are going to dive right into it. Let me exit this. And yeah, I'm going to give you like a minute just to access this link so you can follow along. Yes. So yeah, the link is in the chat. And yeah, let's give it a few seconds. In the meantime, feel free to ask any questions as well.
Sorry, my knowledge is not that deep, but what exactly is this Google Colab thing?
Mm-hmm. Yeah, no, it's a completely fair question. So, so Google essentially has this service called Collaboratory, and what it allows you to do is execute code online without having to put anything on your own computer. So, for example, we're executing Python here. You don't need to install any libraries. You don't need to install the Python interpreter. You can just kind of plug and play immediately, and you use Google's cloud computing just to run it. So the way to access it is you can just literally Google Colab, and open up a new notebook. So it's pretty cool, and it just allows you to run code instantaneously without worrying about any setup, if that helps.
I see. So like you don't need like a editor or compiler on your computer. You just use like Google's Colab, and then like it accesses Google's cloud computing, and then
Yeah,
okay, makes sense.
exactly. I think we have a question in the chat. Does Collab automatically recognize the language, or do you manually set it up? I forget where we manually set it up. I know we can. Usually at the time of creation, you can mention that, oh, I want a Python notebook or an R notebook or a Julia notebook. I don't think there are too many languages that are supported. It's usually Python and R, but yeah. I don't think it allows C++, for example, if that's a question you have.
Oh, okay.
Any other questions?
So if you just start coding, like it'll just automatically like recognize it, right?
I'm pretty sure it will. In fact, if you want to just open up Google Colab here, right, and I say new notebook. Yeah, there we go. So I think if you modify the settings somewhere and you say Colab Pro, GitHub, miscellaneous, I'm actually not sure where you modify it. I'm pretty sure you can Google that. I know that Python and R are supported, but I think Python might be default. That's about it. So yeah, if you want to just start with Python, you can just directly start coding.
Okay.
Awesome. So yeah, let's dive into this code demo. And I just want to mention, like last week, this is going to be a demonstration. It's not really, we're not going to go too deep into what the code means. We just want to kind of prove to you that, hey, everything that we talked about actually does work. And it's fairly simple to implement. We're going to get into the nitty-gritty of the implementation towards the end of the quarter again, a couple of workshops from now. So yeah, let's dive into this. So you want to run the cell and accept. So like last time, we have a few libraries. NumPy is our numerical library, allows us to do math. Scikit-Learn is the machine learning library. It has all these models like linear regression pre-implemented for you. So you can use it kind of out of the box and use it very, very easily. And that's kind of what the cell does, is it brings in all these libraries so we can plug and play very easily. So what we're going to do is we're going to create some dummy data. Okay, we're going to take this line, y is equal to 4x plus 14, and just add some noise to it. So imagine this nice, clean, straight line. We're just going to mess it up a little bit, just permute it a little bit so that it looks a little noisy. And that's what this cell does. So if you visualize it, instead of having a nice, clean, straight line, we have something that more or less resembles a line. You know it's a line, but you don't know exactly what it is. So we want to try and find what this line is. And this cell over here simply splits it into training and testing. Like I discussed before, we train our model on that training data, and then later on figure out how well it's done using the testing data. That's the only distinction that we have. So we have this nice scatter plot, and anyone looking at it is like, hey, this is definitely a line. This is it's definitely not a circle, it's pretty much a line, right? So we're going to decide to use a linear regression model. So Scikit-Learn just says, just call the function linear regression. That's literally it. All that stuff we talked about the last 1 hour of this workshop kind of compresses down into this one function, which is really nice and neat. All we're doing is saying fit it to our training data. The fit function is essentially the training process. The gradient descent process that we discussed it happens under the hood, and it trains our brand new model. So if we run this and we check what the weights and biases are, we're pretty impressed because the weight is 4, which is what we wanted. And the bias is about 13.5, which is also very close to what we wanted. So we wanted to learn a line, y is equal to 4x plus 14, and we got really, really close. So this is kind of proof that, hey, all the stuff that we talked about actually does work. It really does find that line that's kind of hidden behind all this data. And that's kind of the point of what we want to show here is after all this, we get a very, very good and very reasonable guess for what our line is. So there's a metric called the R squared metric. And essentially computes how well our model is done. You can think of it almost as a percentage, and you can say that our R-squared score is 0.96, which is really, really good. Almost as good as we can get. So linear regression for this particular data set worked extremely well. And that's kind of what we want to demonstrate. And we can compute our mean square error. It's about 142. So all we know is that this mean square error has gone down. And this is what we have optimized on. What we can even do further is plot that line of best fit. So we had all this data, and we've computed a brand new line with these parameters, and it goes straight through the data as we'd hope. Okay. Any questions about this demo? Okay, if there are no questions, I'm going to go to another example since we have a little bit of time. And this example is on the diabetes data set. So it's essentially predicting some parameters related to diabetes. And the interesting thing about this is that it's a multi-dimensional data set. So instead of having just one feature value, we have multiple features. And I'm going to do something similar. I'm going to split the data. And the beauty is that we can use the exact same code. We can just say fit. Even if the model has 1,000 parameters or 1,000,000 parameters, all we need to do is say fit it. And Scikit-Learn takes care of it. And we get some parameters, and we get an R-squared score. Now there's an important distinction here. As we can see, the R-squared score is only 0.5, which is not nearly as good as that 0.96 that we had gotten earlier. Why is that? Well, it's a good chance that this data set is just way more complex. Linear regression just doesn't cut it. Now, why did we learn it if it's not that important? Why it's not that powerful? Well, it turns out that linear regression is the building block for every single neural network out there. Not every single one, but almost all neural networks out there. What we're going to do next week is we're going to take this linear regression model, twist it up a little bit, and turn it into logistic regression. Now that is even more powerful. And that, when combined, several thousand of them become neural networks. The stuff that's used in all technology nowadays. This linear regression is that first step, that first building block to kind of understanding those things. And I just want to compute the error here. We get some error value. And that worked out pretty well. So quick note, if you want to try and extend this, you can look at only one of the variables instead of 10. And you can try and plot this and see what kind of lines of best fit you get. But yeah, any questions about any of the code? Okay. If there are no questions, I'm going to head back to the slides really quick. There you have it. Yeah. So like I mentioned, linear regression is extremely useful because it is the building block of so many deep learning models, so many neural networks. And it's kind of critical to understand that really well if you want to go on and continue to study AI. And the next thing we're going to learn, like I mentioned again, is logistic regression, which is used more to classify things rather than to predict continuous quantities. Now, before we close, I want to restart the poll that we had earlier about returning to in-person classes. Since we have a couple more people from back then, in-person workshop, relaunch the poll. And yeah, if you could vote really quick on whether you'd like to return to in-person workshops either next week or next to next week, that would be great. Okay, I'm going to give it like a few more seconds. Okay, awesome. Thank you so much. I'm just going to share the results really quick. It seems like a lot of people want to return to in-person. We'll definitely take that into account and we'll let you know what our plans are. But but yeah, that is our workshop for today. Thank you so much for coming. Definitely check out our workshop next week on logistic regression. Please fill out our feedback form. And yeah, thank you so much.
Can I ask a question?
Yeah, absolutely.
So like I'm a very beginner to like machine learning and stuff, but like this really makes sense. But so like when like someone says like, oh, like you can write like an algorithm to like a machine learning, like I guess like a machine learning machine or software or something like that. Essentially what they're saying is like you are writing all these like mathematical equations to like find the best fit, minimize the loss. And when new data is like fed into it, it like repeats the process. Like based on the new data, it like upgrades and like learns more based on it by like making more like I guess like making that W's and B's like even more accurate and like minimizing losses again and just like repeating that. Is that what they're essentially saying?
Yeah, absolutely. That's again like really, really well said. So in this example, so I want to go back to something you said, right? You said that it's all about these different equations. What all these models differ in, their key aspect is that one equation. So here we had y is equal to wx plus b. In some other ML model, it may be something far more complicated, a far more difficult function. But the principle is the same. It has some parameters and it has some output. So in all models, like you mentioned, all you want to do is update those parameters, regardless of what the function is.
I see. I see. So also like when someone is like literally writing the algorithm, like is this like a coding thing where they're like programming something or they're just writing the mathematical equations?
Do you mean when they're coming up with the algorithm or like actually, kind of deploy it or something?
I guess both, like coming up with the algorithm one and also like creating a machine learning software.
Yeah, absolutely. So when it's coming up with the algorithm, right? A lot of these things are based on very deep mathematics of like optimization and calculus. So a lot of these algorithms have been used in various other fields. And somebody somewhere was like, hey, we could apply this to machine learning and it'll work really, really well, right? So the mathematics is what comes first, almost always, right? And once that's done, they write the code for it. And when they're implementing the model, they kind of keep the mathematics on one side and they kind of translate that into code,
I see.
right? And one more thing to note is that a lot of this becomes very empirical. So you kind of tune the algorithm around and see what works best. So that becomes more practical afterwards.
I see. That makes a lot of sense. Like I like whenever someone says like, oh, algorithm or like machine learning, I used to be like super intimidated. I was just like, what does that even like mean? But I guess like now that I know what happens like behind all of that, it's just like a lot of like mathematical equations and like putting that into like a code to make sure that the program like uses those equations to like make a model out of that data. Okay, that makes a lot of sense. Okay, thank you so much. Like, this is really amazing. Like, I always learn so much. So, thank you so much.
Yeah, you're welcome. Thank you so much for coming.
And also you said the logistic regression is built on top of this, right? The linear regression. So, I mean, we learned like logistic like functions in high school, right? So it's like there are like two asymptotes and it basically looks like an S and it's like starts at the very bottom and like rises and then just like approaches the upper asymptote. So like, could you like give me like a glimpse of like how like linear regression kind of relates to logistic regression? Because like, I can't really visualize how those two are connected.
Yeah, absolutely. So, so you know how the logistic function, okay, let's say we have a function f, which is our sigmoid function, the logistic function like you mentioned, right?
Yeah.
And it's a function of x, f of x. Now, instead of making it f of x, what I'm going to do, I'm going to take the y hat that we had earlier, and I'm going to say it's f of y hat of x. So I'm going to take that y hat and plug it into the sigmoid function. And that's kind of how it plays in.
Oh, so it's like y of, wait a minute, f of y hat of x. Is that what you said?
Yeah, yeah. So we plug the linear regression into that sigmoid function.
Oh, so what that basically does is it just prevents the linear function from going to like extremities.
Yeah, yeah, absolutely. That's definitely one of the uses of it.
Because like, for example, like if you're predicting like midterm score, it's obviously not going to go over 100. Well, except like a very few cases, and obviously it's not going to go below 0.
Yeah, so that's definitely one of the uses. But what we've realized is the more powerful use of logistic regression is to classify stuff. So like we have here, we have cats and we have dogs. One asymptote becomes a cat, one asymptote becomes a dog, and we kind of want to do it in those two classes.
Oh, okay.
Mhm.
Yeah. All right. Looking forward to it. I mean,
Yeah, absolutely.
just like I like learning like algorithm stuff, because the thing is like, okay, like here's all the code and it's like all implemented for you, and all you have to do is learn it. So theoretically you can develop like a machine learning like program without knowing like what's going on. But I don't know, I was like always like dissatisfied by that kind of approach, because like, okay, like I don't know what's going in that black box, and okay,
Absolutely.
so what am I supposed to do? Yeah,
For sure.
yeah, thank you so much. Really looking
Yeah, thanks so much
forward
for
to it.
coming.
Yeah, see you guys next week.
Yeah.